So let us work few problems related with the digital to analog converters and analog to digital converters. Let's start with this problem. The maximum output voltage of a 7-bit digital to analog converter is 25.4 volts. What is the smallest possible change in the output as the binary count increases? So the given digital to analog converter is with a size of 7-bit and it is having the maximum output voltage. This maximum voltage, output voltage, we can name even as the full scale output voltage. Full scale output voltage is mentioned 25.4 volts. Now the question is, what is the smallest possible change in the output as the binary count increases? So we are having total 7 bits. So let us assume the bits B0 to B6. Whenever we are looking, B0 bit is changing 0 to 1. Whenever the B0 bit is changing 0 to 1, it is going to be the smallest possible change at the output. So whenever B0 bit is changing, say 0 to 1 or vice versa, what is smallest possible change in the output? It is a question. So we can look the smallest possible change in the output as resolution into full scale output voltage, and the resolution is defined as it is the change in the output, it is a change in the output whenever binary count, whenever the binary input is changing in 1-bit position at LSB, or you can speak conventionally the definition as resolution is the smallest possible change at the output as and when input binary LSB bit is changing 0 to 1 or 1 to 0. So this smallest possible change in the output may be read as a fraction or maybe read as a percentage. Of course, few authors are looking as a percentage, few authors are looking as the fraction. And in some books, it may be mentioned even simply the resolution as the size of the digital to analog converter. The size of the digital to analog converter here, it is a 7. So in some of the books, you may be looking even as the resolution as simply 7. So basically, we are talking conventionally the definition. Resolution is the smallest possible change in the output as and when there is a change in the LSB bit at the input. We can have the resolution as 1 upon 2 to the power of n minus 1. It is as a fraction. And if you want to look as a percentage, it will be into 100. And coming to this, we are talking here the fraction or the percentage without units. Coming to this here, we are talking the smallest possible change in the output voltage. Even in some of the books, the resolution may be mentioned even in terms of the units voltage or current. So in that case, the resolution is the smallest possible change in the output voltage or output current whenever input binary bit is changing. So anyway, if you look here, conventionally it is 1 upon 2 to the power of n minus 1 into full scale based on the values of the given problem. N is 7, so that 1 upon 127 into full scale output voltage we are looking as 25.4 volts. Hence it is coming to be 0.2 volts. Hence it is the answer. So that as and when binary bit is changing 0 to 1 or 1 to 0, the change in the output voltage is 0.2 volts. So let us go to the next problem. So let us look to the next question. For designing of a digital to analog converter which can have a resolution of 5 millivolts and the full scale voltage is to be 8 volts. Then the question is, how many number of bits are required for this digital to analog converter? So how many number of input digital bits are required for this digital to analog converter? So we want to design a digital to analog converter, and this digital to analog converter need to be with a resolution of 5 millivolts. So I was talking the resolution sometimes by few authors may be mentioned in terms of the smallest possible change in the output voltage or output current. Whenever input binary bit LSB is changing, maybe 0 to 1 or 1 to 0. In this case, it is basically the smallest possible change in the output voltage, that is 5 millivolts. And is mentioned the full scale output voltage. The digital to analog converter is having the full scale output voltage of 8 volts. The full scale output voltage is nothing but whenever all the bits are at the input, when all the input bits are 1, correspondingly the equivalent analog output voltage is 8 volts. Then we are looking at a question, how many number of input digital bits are required for this digital to analog converter? The equation will be delta V naught equal to 1 upon to the power of n minus 1, where n we are talking the number of input digital bits into full scale output voltage. It is mentioned delta V0 5 millivolts, so that 5 into 10 to the power of minus 3, 1 upon to the power of n minus 1. Full scale output voltage is 8 volts. So to the power of n minus 1 is 8 by 5, 10 to the power of 3. So we are looking to the power of n is 1601. This n, number of input digital bits, this n is an integer. If at all n is 10, if at all n is 10, we are coming up to only 1023. So with n is 10, it is not possible. So next higher value is 11. So as I said already, n must be integer, it is not a fractional value. Next higher integer is coming to be 11, which will satisfy whenever n is 11, we can go up to 2047. So it is in the range, hence the number of input digital bits required for this digital to analog converter is 11, hence it is the answer. So let us go to the next question, is the third question. A 5-bit digital to analog converter is having the output current of 10 milliamperes for a digital input of 10100. So the given digital to analog converter is the size of 5 bits and it is having the output signal as a current signal. So for the digital input of 10100 for this digital input, the corresponding analog output current is 10 milliamperes. One bit, a bit is, what is the output current for the digital input of 11001? So we are looking for this 11001, what must be the equivalent analog output current? It is 1 bit. Second bit is, what is the maximum output current, that is full scale output current? It is the second bit. Let's go for first bit first. You can see an equation while discussing the digital to analog converter theory. We mentioned output analog signal is equal to k into to the power of n minus 1 b n minus 1 plus to the power of n minus 2 b n minus 2 and so on to the power of 1 b1 plus to the power of 0 b0. It is the equation we may named as A. So this equation required for us to use now to work on this problem. And we know well, this total polynomial equation what we are looking with the parenthesis, this is nothing but converting the binary number as equivalent decimal number. This total parenthesis is nothing but converting the binary data to decimal form basically. So for this digital input, if you want to look what is the output current, to recognize what is the output current, basically we need to know the proportionality constant k value. From the given data, let us check whether it is possible to find the proportionality constant K value or not. It is a given digital input. For this given digital input, we are looking the output current, what we are reading, it is mentioned in the problem. So knowing for this digital input, the output current, we are having a possibility to recognize what is the proportionality constant. While knowing that, of course, we can try for this. So let us look first the proportionality constant. So 10 milliamps, K it is unknown, and for this, if at all we are looking to equivalent decimal value. Equivalent decimal value is 20. So in the parenthesis place we are putting 20, which is giving K as equal to 0.5. It is a proportionality constant, of course it is in milliamps. Now coming to this question. So for this we are having the equivalent decimal value is nothing but 25. 11001 decimal value is 25. So while looking to this decimal value 25, we can look the output current as equal to 0.5 milliamps into 25, which is giving 12.5 milliamps. And coming to B bit, the B bit is the case, what is the full scale output current? So the full scale output current will be having whenever all the bits are 1. Whenever all the bits are 1 for this 5-bit case, it is nothing but decimal 31. So the full scale output, if at all we are looking, it is K, it is 0.5 into 31, which is giving 15.5 milliamps. So it is the answer to the B bit. We are looking here in the given question, the analog output is in the current form. So we are reading the outputs in the currents. If at all the analog output signal is in the voltage form, of course even for that we will be using the same equation. So the readings will be having in terms of volts. Let's go to the next question. Of course it is related with the analog to digital converter. Till now the first 3 questions we were discussed of digital to analog converter. If you look here, the resolution of a 4-bit counting type, that is counter type ADC, is 0.5 volts. For analog input of 6.6 volts, what is the digital output of the analog to digital converter? It is a question. So we are looking here, the analog to digital converter is having size as a 4. It means whatever the analog data which is converted to the digital form, which is going to be represented by using 4 digital bits, by using 4 binary bits, and it is having the resolution, as 0.5 volts. So the resolution in the case of analog to digital converter is defined as the smallest possible change in the input analog signal, which will give the effect for the digital output LSB bit. The smallest possible change in the analog input signal, which is going to give the effect on LSB bit of the digital output, that we are going to define as a resolution. It means, suppose 4-bit case, the bits are B3, B2, B1, B0. These 3 bits remain same. It must be remain same as it is, but B0 has to change, say 0 to 1. For change of the B0, 0 to change, what is the smallest possible input signal we need to change? So this input signal may be a voltage signal, may be current signal, so the one which is going to be converted to the digital form. So what is the smallest possible change in the input analog signal which is giving the effect on the LSB bit? May be changing 0 to 1, or you can say vice versa, 1 to 0. That we are defining as the resolution of analog to digital converter. So we are looking here, the resolution is a 0.5 volts, means LSB bit is going to affect whenever the input analog voltage is changing an amount of minimum 0.5 volts. Now we are looking at a question. For an input analog signal, the input analog signal voltage signal, of course 6.6 volts, what is the digital output is the question. So you can see now the number of steps required to reach to number of steps required by this analog to digital converter to reach to 6.6 volts with a rate of 0.5 volts. So if at all you are looking here, it is coming to be 13.2. So we are looking here the readout only in the integer form. So the readout will be corresponding to the decimal 13. Hence the digital output will be 1101. It is the answer. It was the question in the 99 gate exam. A 16-bit counter type analog to digital converter is driven by 500 kHz clock. So we are having a analog to digital converter of the counter type, and in the system we are having the usage of 500 kHz clock. The question is, we need to calculate the maximum conversion time, second bit the average conversion time, the third bit the maximum conversion rate. So the clock which is used in the analog to digital converter is frequency of 500 kilohertz, so that the clock time period will be 1 upon 500 kilohertz. Hence it is coming to be 2 microseconds, and we are having first bit maximum conversion time. It is the first. The maximum conversion time for counter type analog to digital converter is given as 2 to the power of n minus 1 into clock time period. It is given, it is a 16 bit, so that we are looking n value is 16, and clock, of course, we are having the repetition time 2 microseconds. Hence 2 to the power of 16 minus 1 into 2 microseconds, which is giving the value as 131.072 milliseconds. So it is a maximum conversion time for the 16-bit analog to digital converter of counter type. The second bit we are looking average conversion time. The average conversion time we are having a calculation. The maximum conversion time divided by 2, that is 131.072 milliseconds by 2. So 65.536 milliseconds. So it is the answer to the second bit. The third bit we are looking maximum conversion rate. The maximum conversion rate is 1 upon maximum conversion time. So 1 upon 131.072 milliseconds. So conversions, how many conversions per second? It must be integer. So we are looking 1 upon 131.072 milliseconds, 10 to the power of minus 3. So that we can look as 10 to the power of 3 divided by 131.072. So if we look here, it is coming exact value 7 point something. It is coming to be 7 point some values. But we are bothering only how many conversions per second, integer value. Hence answer is 7 conversions per second. we must go for lower side, not higher side. We should not go for 8, we must go only for 7. But we are going to 8, it is exceeding more than 1 second. We have to look within the 1 second how many conversions are possible. Within the 1 second, 7 conversions are possible. Hence the answer is lower side 7 conversions per second. Let us go to the next question. It is also related with the analog to digital converter. An 8-bit successive approximation analog to digital converter has full scale reading of 2.55 volts and its conversion time for input of 1 volt is 20 microseconds. What is the conversion time for a 2 volts input is the question. So we are looking, it is successive approximation type ADC. For a successive approximation type of analog to digital converter, for any digital readout, the conversion time is uniform, conversion time is same. Whether the readout in this example for 1 volt it is given as 20 microseconds. So even for 1.5 volts, even for 2 volts, even for 2.5 volts, the conversion time must be same. Hence, answer for this question, the conversion time for converting 2 volts input is same 20 microseconds. The conversion time is uniform for any analog input. For the case of successive approximation type of analog to digital converter, as long as it is within the range, the digital readout may be of anything, the conversion time must be same. Hence, answer is 20 microseconds. So find the resolution and the percentage resolution of an 8-bit analog to digital converter which is having input voltage range -5 volts to +5 volts. We are looking here, this analog to digital converter size is 8. So the digital readout will be with 8 bits and it is having the voltage range at the input -5 volts to +5 volts. So that resolution, if you look, resolution will be minus of it will be +5 minus of -5 volt +5 volts minus of -5 volts divided by 2 to the power of n minus 1. So that it is coming to be 10 divided by 2 to the power of 8 minus 1. Hence 10 divided by 2 to the power of 8 minus 1 is nothing but 255. If you work well, it is coming to be 39.22 millivolts. And if you look to the percentage of resolution, the percentage of resolution will be, I think it is coming 0.3922 percentage. So resolution is 39.22 millivolts and percentage of resolution will be 0.3922 percentage. A 10-bit analog to digital converter with a full scale output voltage range, the full scale output voltage of 10.24 volts is designed to have a plus or minus LSB/2 accuracy. If the ADC is calibrated at 25 degrees centigrade and the operating temperature range from 0 to 50 degrees centigrade, then the maximum net temperature coefficient of the ADC should not exceed. It is a question, it was one of the GATE exam paper question. These are the options. So you can see 1 LSB is 1 upon 2 to the power of 10 because size of ADC is 10. So that it is coming to be 0.000997 and accuracy plus or minus LSB by 2. So that 0.00 0.0997 by 2. It is 0.000488. So that it should not exceed 488 microvolts per degree centigrade. Hence, it is the answer. Answer is option B. Answer is option B. The circuit shown in the figure is a 4-bit digital to analog converter. So, a 4-bit digital to analog converter circuit is given. A 4-bit digital to analog converter is given. So, this 4-bit digital to analog converter, based on the figure, it is possible to recognize it is a weighted resistor digital to analog converter, so that it is B3 bit, it is a B2 bit, it is a B1 bit, it is a B0 bit. And we are looking the feedback resistor output to the inverting term of the op amp is the resistor value of R. It is mentioned the circuit shown in the figure is a 4-bit digital to analog converter. The input bits 0 and 1 are represented by 0 and 5 volts respectively. So, the logic 0 value is a 0 volt, the logic 1 value is a 5 volts. The op amp is ideal. So, it means it is having high input impedance and low output impedance, so and so. But all the resistors and 5 volt input have tolerance. These resistors what we are using, and for representing the logic 0 and logic 1 volt, what is the supply voltage we are having? The supply voltage and the resistors are with a tolerance of plus or minus 10%. The question is now the specification for the digital to analog converter. The specification for the digital to analog converter, basically the specification we want to give what is the tolerance. So, that is to be rounded to the nearest 5% as per the question. So, these are the given options. If you look to the solution to this problem, it is a weighted resistor digital to analog converter. The weighted resistor digital to analog converter, the proportionality constant, if at all we are looking to the magnitude, the proportionality constant is given as V reference, that is a 5 volts, into R reference by to the power of n minus 1 into R. It is the equation V reference into RF divided by to the power of n minus 1 into R. So, here in our question n is 4, hence you can look to the K as V reference into RF divided by 8 into R. We know here RF is R. If at all we are having 0% tolerance is 0. It means the resistors are with exact value, supply voltage 5 volt also exact value, and V reference is plus 5 volts. In that case, K value, if at all we are reading, it is coming to be 5 into R divided by 8 into R. Hence, it is nothing but 5 by 8. It is nothing but 5 by 8. Now, the question is, what is the specification for this digital to analog converter in terms of tolerance? So, what is the maximum error you can say based on this given data? The tolerance, if at all we are looking, one possibility, whenever K value is coming to be the highest possible value, corresponding to this there is an error something, and there is a possibility whenever k is coming to be lowest possible corresponding to that what the deviation from the exact value. Suppose if you take exact value is x, that is 5.8 corresponding to the distal data of so and so. So we have to look one case. Case 1 is whenever kx is more positive value. Whenever k is more positive value, you can look here, the k will be coming to be, V reference will be upper side. It is a plus or minus 10%, plus or minus 10%, plus or minus 10% means higher side you have to look, higher side is coming to be 5.5. And the feedback resistor also positive side because of the x higher value 1.1 into R. 10% means here 8 and this R will be the lower side. The lower side will be 0.9 R. Hence we are looking this value is nothing but 6.72 divided by 8. So it is coming to be 6.72 divided by 8. Based on this, if you look, what is the error? The error is coming to be 6.72 by 8 minus 5 by 8. It is coming to be 1.72 by 8. So this 1.72 by 8 is the error which is deviating from the expected value of 5 by 8. So that we can look for 5 by 8, the deviation we are looking 1.72 by 8. For percentage we are looking for 100%, how much? It is coming to be 1.72 by 8 divided by 5 by 8 into 100. So this is coming to be 34.4%. So when you are rounding to nearest to 5%, then it is coming to be 35%. When we are rounding to the nearest percent, it is coming to be 35%. So this is one case. The other case we are having a possibility, that is a case 2. We are looking x will be the lowest possible. The x will be whenever the lowest possible k value, if at all we are looking, this k value if you look, the V reference must be lower side. Lower side find means it must come to 4.5. And R reference also lower side, then it is coming to be 0.9 R. And by 8, this R will be higher side. It must be 1.1 R. Then it is coming to be the x is deviating from the expected lower side. So corresponding to this, if at all you are looking, it is coming to be some 1.318 by 8. And with this, if at all you are looking, this is coming to be 3.68 by 8. And if at all you are looking at the difference, that is 5 by 8 minus 3.6 by 8. If at all you are looking to this case, it is coming to be some 1.318 by 8. And with this, if at all you are looking to the percentage, it is coming to be around 26. And when you are rounding to 25%, because the nearest 5%, it is one possibility. So among these two, when it is taking x higher side, when this x is moving higher side, the tolerance is coming to the higher value comparing to the case, worst case, when x is going to the lower side. Based on this, what is the maximum tolerance of this digital to analog converter if at all we are looking? The maximum tolerance will be this. Hence, the answer will be option A. The worst case if at all you are looking, worst case is a case now whenever x is taking x, we are taking the exact value, the deviation to the higher side, whenever x is going to the higher side, then it is going to be the maximum tolerance. So the maximum tolerance we are looking for this digital to analog converter of size 4 bit is 35%. Hence option A is the answer.